big fish, and I want to say something about them. Before I go into any detail of that, I want to say something about the other end of the title of this subject, this lecture, which has to do with how big is infinity. And well, some of you may well know there's a theory of sizes of infinity due to Georg Cantor, which is a wonderful theory, I say, one of the most incredible achievements in mathematics. But what I want to tell you hasn't really got anything to do with that. So it's something quite, in some sense, more elementary. In fact, it's very elementary to begin with. I want to talk about large numbers, and one way of getting numbers to be big is to start raising some number to another power. Of course, if I raise a to the power b, that means you multiply a by itself a total of b times. So that's a very familiar notion. Now, I want to consider what I mean by raising a to the b to the c. What does that mean? Well, you could bracket it two different ways. You could say it's a to the b to the c, or a to the b to the c. Well, it's actually pretty clear it's got to be a to the b to the c, because the other one, you don't have to use double exponents. It's just a to the bc, so we'll forget that one. It does mean this. Now, I want you to note the fact that with large numbers, if a, b, and c are fairly large, then this quantity here usually doesn't really depend much on a. In fact, it doesn't depend a great deal on b. The only thing you really need to know is c. If you, for example, as we actually come across this number, I hope, if I get to that part of the talk, a very large number, 10 to the 10 to the 123, which sort of refers to how unlikely the Big Bang was. Nevertheless, it seems to have been there, but I'll say what I mean a bit more about that. But the thing is, I tend to write it 10 to the power 123, when it should have been e to the power 10 to the power 123, where e, this thing called the base for natural logarithms, is this thing here with an infinite decimal and all that. But if I wrote it this way, I'd have to explain what e is. Of course, the physicists and mathematicians here know perfectly well what e is. That doesn't mean that everybody in the audience knows what e is. So if I write it with a 10, then that's sort of, I don't have to explain what e is. But you see, it doesn't really make any difference, because if I write 10 here or an e there, as I say, it doesn't much matter what the bottom exponent is, but the top exponent is only mildly changed, you see. Not 123, it's 123.2. But this number is pretty inaccurate anyway. It's probably really only 124, 125. Depends on whether you take into account the dark matter, which I didn't in that formula there. And most of the actual matter in the universe is dark matter, and then there's dark energy too, which I prefer not to call it that. But anyway, so it doesn't come into this formula. But nevertheless, that's just giving you a feel for the fact that it's the top exponent that is the one that really counts. But that's not so much that I'm really interested in here. What I'm a little more interested in is the question of what happens when those numbers are infinity. So I'm going to allow the numbers e and 10 and so on to be infinity. Now, what does that mean? Well, you see, what I'm talking about here will be the question of functional freedom. You see, suppose I asked the question, how many magnetic fields are there in space? How many different magnetic fields, you see? Well, I'm talking about fields, and a magnetic field is just a good example of a physicist's field. It's not a mathematician's field, which is something completely different, but never mind. But if it's on a space of d dimensions, what you have to think of, well, if it's a magnetic field, you see at each point in your space of 3 dimensions, there will be an arrow pointing which way the magnetic field is pointing, and that length of the arrow will tell you how strong the field is. So you've got to think of how many different ways are there of putting these arrows, one at each point of space, in a continuous way. So they've got to be done continuously. And this is a notation that, as far as I'm aware, was due to John Wheeler, to write this number of how many different fields there are as infinity to the, well, 3, and this just corresponds to the number of components of the field. In the case of magnetic field, it's 3 components per point. And this 3 over here refers to the number of dimensions of space. And that is that's how you write the number of magnetic fields there are in space. Now, if you just wanted to say how many points are there in Euclidean space, then you would write, now for some reason the 3's got left off here. I probably wrote it wrong and rubbed it off and then forgot to put it back again. So imagine a 3 there. If I have my pens, I could put it back, but don't worry about it. So there are infinity cubed points in Euclidean space. But more generally, you could write a number like this, which describes how many continuous entities there are. And this is not the same as Cantor's theory, because I'm talking about continuous equivalence, and that makes a difference. So this would be the number of k-component fields in a space of d dimensions. And the point that it's really very much like this, that the number that's really important is the d up here. Okay, if you're trying to compare 2 numbers like this, and you want to know which one is bigger, and the d happens to be the same, okay, then you look at the k. But if they're on different dimensional spaces, that completely swamps everything else. Now, how do we see that? Well, this is a good way of looking at it. Think of a toy model where I replace r. R means the space of real numbers. So you see, when we're talking about magnetic fields, we have a thing which has 3 real number components. So you think of a right-handed frame or something, and your vector, and you take the 3 components in those 3 directions. So you've got 3 numbers which would characterize the field. So at that point. But suppose the real numbers that you use, well, you could use it in 2 ways. You could use it in describing your space, or you could use the real numbers to describe the components of the magnetic field. But let's replace that system of real numbers, which is this funny r here, it means the real numbers, by some finite set n. N could be a large number. Very, very large number, imagine. So we say it's n instead of infinity. And then you say, how many k-component fields are there at any point in the space? Well, you see, you have n to the k numbers to define the field at each point. That's n numbers for each component. You've got k components, so that's n to the k numbers. At each point, and n to the d points. So at each point, you've got n to the k numbers, and that's, all these things are a bit confusing, but all it's saying is that you have altogether the number of different ways of doing that are n to the k to the n to the d, which is n to the k n to the d. And now you let n go to infinity, and that gives us this Wheeler-type notation. So that's a good way of thinking where it comes from, if you like. Okay, and this is the sort of thing that leads me to have trouble with string theory, and I'll come to that shortly, or in a little while, because in at least modern versions of string theory, the number of dimensions of the space that is used is not our usual 3 space, 3 numbers of 3-dimensional space, and 1 of time, but in fact nowadays, well, 9 or 10 spatial dimensions and 1 of time.